We are ready to begin reviewing for Unit Test 3. This is the end of Block C, which runs from weeks 9 to week 12. The test is due at the end of week 12, Sunday at midnight. However, you do have until the end of week 13 before we reach the hard deadline, at which time all Block C assignments and Unit Test 3 should be complete. As with other tests that we have done, this will be one test in two parts. The first part is comprehension. It is the traditional multiple choice, true-false, and matching test. This portion of the test uses the Respondus Lockdown browser, which means you should not have any notes, calculators, or any other material with you when you complete this portion of the test. All of the calculations will be on the applied portion of the test. You should complete an answer sheet before you begin the applied portion of the test. This is where you will use statistical software. And the applied portion of the test does not use the Respondus Lockdown browser, allowing you to have that answer sheet at the ready when you work on this portion of the test. So let's review. What did we learn in Block C? We're going to begin with some information about correlation. Correlation, as you can tell from the name, is about relationships, specifically the relationship between two variables. When variables are related, then changes in one variable are consistently associated with changes in another variable, such as in the case of a positive correlation, where both variables move in the same direction, so that as one variable increases, the other also increases. A positive correlation would also occur when, as one variable decreases, the other also decreases. They move in the same direction. So in an example of us selling concessions during a football game, as temperature goes up, the amount of cold soda that we sell would also increase. We can contrast this to a negative or inverse relationship between variables, where the variables move in opposite directions, such that as one variable increases, the other decreases. So now, at a football game, when we are working the concession stand, as temperatures increase, the amount of hot chocolate that we sell decreases. But as temperatures get colder, then the amount of hot chocolate sold increases. Those two variables move in opposite directions. We can also concern ourselves with the strength of the relationship or the strength of the correlation between the two variables. This is defined as the extent to which any given x value is paired with one and only one y value. When the relationship between two variables is perfect, then the correlation would have a value of either +1 or -1, and all of the dots would appear along a straight line. When a correlation does not exist, or the correlation is 0, then the relationship between those two variables is non-existent. Therefore, correlations close to 0 are weak, and they become stronger as they approach either +1 or -1. This is an example of a correlational coefficient, which we call R. Now, R in the correlation actually stands for regression. And it reminds us of that regression line, or line of best fit, that runs through a scatter plot of the dots. So R, the regression value, equals something with a sign. The sign indicates the direction of the relationship, either positive or negative, and an absolute value. The absolute value indicates the strength of the relationship. Absolute values closer to 0 are weaker. Absolute values closer to 0.9 or 1 would be stronger. We can square the correlation coefficient to get a coefficient of determination, which is the effect size for the correlation. We call it R squared. It's the squared value of the correlational coefficient R. This coefficient of determination tells us the proportion of variance in one variable, specifically the y variable, explained by variance in the other variable, the x value, or predictor. So if we were talking about the relationship between burnout and job satisfaction, we might say that the effect size for burnout, with an r squared of 0.42, indicates that a large portion of the variability in job satisfaction, specifically 42%, was accounted for by the level of burnout that a counselor had experienced. We should remember that correlation does not imply causation. There is no cause and effect relationship being tested with correlation. Correlation also does not test for differences between variables. If we want to look for differences, we'll use tests like the F-test, ANOVA, or a t-test. Correlation does not predict outcomes. That's the next step. We will use simple linear regression and multiple regression to predict outcomes. Correlation is just looking at relationships. And the order of the variables doesn't matter for the correlational coefficient. If you get a correlation between x and y, you will get exactly the same correlation if you were to compare y and x. Next, let's look at something very closely related to correlation, scatterplots. This is an example of a scatterplot. We've plotted height on the x-axis against weight on the y-axis. Each individual in our study who has had their height and weight measured is represented by a single dot. And running through that cluster of dots is the regression line. So the scatterplot graphically displays the strength and the direction of a correlation. It's depicted with those dots, or data points, which show scores on one variable, height, plotted against scores on a second variable, weight. Each data point is a pair of x and y scores. And the n, the sample size, is the number of pairs of x and y scores. So you, as an individual, would have a height and a weight. The pair of those two scores come from you. You are one person, so n equals 1 for that pair. We should also be alert to where we place these variables in the scatterplot. The predictor variable goes on the x-axis. The outcome variable goes on the y-axis. So if we are predicting weight from height, height is our predictor, weight is our outcome. That line running through the middle of the dots is the regression line, also called a trend line, and that single linear relationship visualizes the relationship between those two variables. So the regression line is sometimes called the line of best fit. It runs like a mean through the middle of those dots. It's important that you create a scatterplot before you calculate a correlation so that you can see the pattern of the relationship between the variables. And this will give you a lot of useful information as you begin. When a correlation is strong, as the R value, the correlational coefficient, is closer to either +1 or -1, all of those data points will be very close to a straight line. This means that the variability between those values is low and the relationship is strong. A weak or moderate correlation, as our correlation coefficient approaches 0, is represented by a more elliptical pattern in those dots. They are further from the line. There is greater variability. The relationship between the variables is weaker. If there is no correlation between x and y, then the correlational coefficient would equal 0, and there would be no relationship between the variables. We would see no linear trend, and the scatterplot itself would be elliptical or circular or cloud-shaped, where we would not be able to draw a line in any particular place that would represent a relationship between those variables. If there is a relationship between the variables, we can use that relationship for prediction, and that is what we call simple linear regression. It is a way of predicting an unknown y score based on x values from a correlated variable. Perhaps we're interested in whether SAT scores predict grades in college. Now, if those variables are uncorrelated, if the correlational coefficient between them is close to 0, then X will not predict Y. So there would be no reason to do a linear regression on uncorrelated or unrelated variables. If, however, there is a correlation, we could use the X value to predict Y. And we will represent a predicted Y value as Y hat. Now, since the X is being used to predict, we call it the predictor variable. The scores that we are predicting, the Y variable, would be called an outcome variable, a dependent variable, or sometimes a response variable. The linear regression line, that straight line running through the cluster of the dots, summarizes the relationship between X and Y. And it is what we will use to predict any subject's Y score, Y hat, at any given X value. So in this predictive model, if I know your age, I could predict your height. I would go across the X-axis until I got to your age, let's say it's 8 years old, and I would go up to the line, and then across to the Y-axis, and I would get a value somewhere close to 54 inches. If I know your age, I predict your height. The equation that we will use is Y hat equals either B sub 0 plus B sub 1 times X, or we will use Y hat equals A plus BX. Both of these are the same way of depicting the straight line. We can either use a beta 0 or we could plug in an A to represent that exact same value. I'll also mention that the Y hat is sometimes written as Y prime. Again, it always represents a predicted Y score. So the Y hat is the predicted value. That is your height that I have predicted from your age. It's a predicted value from that equation that uses the straight line. The A, or the B sub 0, is the y-intercept. So this would be the value of y when x equals 0. Go all the way to the left on your x-axis. Where the straight line crosses the y-axis, that's the y-intercept. The slope is the straight line. The slope is actually change in x versus change in y. And a raw score in our straight line equation is used for prediction. So let's dig into that a bit more deeply. Using our equation for the straight line, let's focus first on either a or b sub 0, the y-intercept. So this is the value of y when x equals 0. It's the point at which the straight line, the regression line, crosses the y-axis. This is called the constant in our equation. It is our starting point. The slope is the steepness of that regression line, and it tells us both the direction, positive or negative, and the rate of change for the relationship between the variables. The steeper that line becomes, the greater the rate of change between those variables. The closer it is to a flat line, the slower the rate of change between the variables. There are some assumptions when we are using regression. The first is linearity, that there is a linear relationship between the two variables. That's the idea of correlation. If the variables are correlated, there is a linear relationship. We can use those variables for regression. But if there is not a correlation between the two variables, then there's no point in using those values for regression because there is not a linear relationship. Now, we can have a relationship that is too strong. Multicollinearity is something that we run into, especially with multiple regression, where we have multiple predictors, where two predictors are essentially the same. They're predicting the same thing. They are so closely correlated that we don't need both of them. We can just use one of them. Multicollinearity is this undesirable correlation among several independent variables. And the solution for multicollinearity is to choose one independent variable and ignore the other. There's also an assumption of independence of observations. Now this we see when we examine the output of our regression and we look at the residual errors. Those should be independent, and I'll show you an example of that here in a moment. Another assumption for regression is homoscedasticity. That means that the variance of all those residual errors should be the same across all values of a predictor, and we can look at that as we examine the output for our regression equation. And then finally, outliers. If we have outliers in one or both variables, that can distort both the direction and the strength of a correlation. So what is an outlier? An outlier is an observation whose residual is much larger than the rest of the residual values. And when we find outliers, in most cases, the thing that we have to do is to exclude those outlier cases from our analysis. We can do simple linear regression, or we can make our model more complex. And for that, we use multiple regression. You see, simple linear regression is one independent variable and one dependent variable. It's really very similar to correlation, which correlates two variables at a time. But multiple regression allows us to use two or three or more independent variables to predict one dependent variable. So we can have several independent variables, but we will only use one dependent variable. Now, each independent variable contributes either, or both, a B, which is the unstandardized regression weight, and a beta, which is the standardized regression weight. So let's recall what those are. The regression weight for a standardized variable is called a beta weight. It's represented by the Greek letter beta. Now, typically, if we're comparing the relative contribution of, let's say, three independent variables, but they're measured on different scales, it's really difficult to compare the relative contribution of those variables. So the solution then is to standardize those variables, transforming them into a comparable scale. Therefore, standardized regression coefficients, or beta, are comparable, but the unstandardized regression coefficients, those that are still in their original scales of measurement, generally are not comparable. Finally, we want to talk about model fitting and examining the assumptions and the residuals to find out whether our assumptions have been violated, and if so, what we should do about it. So the values of the multiple regression error terms are assumed to be independent of each other, normally distributed, and to have a mean of 0. We would examine a scatter plot of our residual values, the error values left over at the end of our regression equation. They should be roughly elliptical, and if so, that indicates that the assumptions of the regression equation have been met. The mean of 0 is represented by that straight line that runs horizontally from the y-axis at a value of 0. You can see it says regression standardized residual, and the straight line runs right across 0. So this would be an example of a scatter plot of residual errors that is good. It's showing us that the assumptions for our regression equation have been met. We should also examine our dependent variable to make sure that it is normally distributed. And in this case, we see that the histogram of the dependent variable roughly follows that normal curve, so that is good. The distribution of the independent variables, however, doesn't affect the regression model. It's really only the dependent variable that we want to check on as we look at this assumption of normality. And then let me mention a few other details about the types of variables that can be put into a regression equation. Qualitative variables, as opposed to the quantitative variables, quantifying height or weight or age. Qualitative variables are the ones that are not measured by how much or how many. Instead, a qualitative variable is assigned values that represent categories. And one way that qualitative variables are commonly used in a regression equation are to put them in the form of what we call dummy variables, a variable that takes on the values of 0 or 1. 0 or 1. The 0 means not present, and the 1 means it is present. So we're creating a category that is just bifurcated to 0 and 1. This can be used to incorporate the effects of qualitative variables in a regression model. Very difficult to use qualitative variables that are categorical and ordinal. We'd like to get them down to just those two bifurcated variables. So let's wrap up talking about what you need to know for the applied section of the test. You will be given an Excel dataset called PGA driving distance, and you will do a correlation, a simple linear regression, and multiple regression. And for this, you will use JASP. I have included some very detailed instructions on how to do correlation, simple, and multiple linear regression. You will find those instructions in Unit Test 3 JASP Regression.pdf, which is available through Blackboard for the course. This can be used on the test, and in fact should be used on the applied portion of the test. And again, there will be no lockdown browser, so you won't be dinged for using extraneous materials while you're working on this portion of the test. The study guide that you should use to prepare for the multiple choice, true, false portion of the test, however, cannot be used because that portion uses the Respondus lockdown browser, and it would ding you for having some extraneous material available as you're taking the test. This is an example of the simple and multiple regression in JASP worksheet that will explain the data, what each of the data variables mean, and how to work through the simple linear regression, multiple regression, and correlation that you will need for answering. I wish you the very best on the test. Remember, to stay totally on track, you should be wrapping up this test at the end of week 12, but you do have until the end of week 13 before you reach that hard deadline in which the test must be completed. Good luck. I hope that you do well.